Hey everyone, and welcome to this power-packed revision session. Today, we're tackling Chapter 10, Halogen Derivatives, a chapter that is absolutely crucial for your exams. Don't worry at all, we're going to make everything crystal clear.
I know. This chapter can feel a little tricky sometimes, but I promise you, in the next few minutes, we are going to master every single concept. So grab your notes, get comfortable, and let's get ready to absolutely ace this.
Okay, so here's our game plan. We're going to start with the absolute basics. Then we'll learn the rules for naming these compounds, check out the most important preparation reactions, then get to the heart of the chapter, the reaction mechanisms, and we'll wrap up with a fascinating twist into the 3D world of molecules. Ready? Let's go! First things first, building a strong foundation is key. So let's start by understanding what these halogen derivatives actually are.
It's actually really simple. Just take any hydrocarbon, like methane for example, and swap out one or more of its hydrogen atoms with a halogen atom. That could be fluorine, chlorine, bromine, or iodine. And that's it. You've just made a halogen derivative. Simple as that. Now we classify them based on the type of carbon the halogen is attached to. This gives us four main types. If it's on a single bonded carbon chain, that's an sp3 carbon, it's a haloalkane. If it's on a carbon with a double bond, an sp2 carbon, it's a haloalkene. On a carbon with a triple bond, or sp carbon, it's a haloalkyne. And if it's attached directly to a benzene ring, we call it a haloarene.
This is a concept that always comes up in exams, identifying primary, secondary, or tertiary halides. The trick is simple. First, find the carbon that's directly bonded to the halogen. Then, just count how many other carbon atoms are directly attached to that carbon. If it's 1, it's primary, 2, it's secondary, and 3, it's tertiary. Easy marks, right?
All right, now that we know what they are, let's talk about naming them. In organic chemistry, getting the name right is half the battle for scoring well, so let's quickly master the IUPAC rules.
There are two main systems, common names and IUPAC names. For the common name, you first name the alkyl group, then add halide, like ethyl bromide. But the IUPAC system, which is the standard, treats the halogen as a branch or a substituent and uses its name as a prefix. So ethyl bromide becomes bromoethane. For your exams, IUPAC is definitely the way to go.
Let's look at some examples to really nail this down. See, CH3CH2Br has the common name ethyl bromide, but its IUPAC name is bromoethane. Similarly, the common name for CH3,3-CCl is tert butyl chloride, but its proper IUPAC name is 2-chloro-2-methylpropane. Just remember to always find the longest chain and start numbering from the end that gives your substituent the lowest possible number.
Okay, let's head into the lab. Well, figuratively. This section is all about the recipes, the essential named reactions used to create halogen compounds. These are super important for your exams, so pay close attention.
First up, the Lucas reagent. It's a mix of concentrated HCl and anhydrous zinc chloride. Its main job is to make alkyl chlorides from alcohols. But here's the cool part. It has a bonus use. A tertiary alcohol reacts instantly. A secondary one takes a little time, and a primary alcohol doesn't really react at room temperature. So it's not just for preparation, it's a test too.
Now what if you want to make an alkyl iodide? The Finkelstein reaction is your best bet. The key idea here is that it's a simple exchange. You take an alkyl chloride or bromide and react it with sodium iodide and acetone. The sodium chloride or bromide precipitates out, which means it becomes a solid and we can easily remove it, leaving us with our alkyl iodide. Swap and done. And for alkyl fluorides? For that, we have the Schwarz reaction. This is the go-to method for making fluorides. Again, we're doing a halogen exchange, but this time with a metallic fluoride like silver fluoride. It works on the same principle. The silver chloride precipitates out, and we get the alkyl fluoride we wanted.
Okay, people, it's time. We've arrived at the main event of this chapter, SN1 versus SN2. If you can understand this, you've pretty much cracked the most important part of halogen derivatives. So, full focus here.
Let's start with SN2. The 2 stands for bimolecular. This means the rate of the reaction depends on two things: the substrate, which is your alkyl halide, and the attacking nucleophile. It all happens in a single concerted step. The nucleophile attacks from the back, while the halogen leaves from the front, kind of like an umbrella flipping inside out in a strong wind. This flip is called inversion of configuration.
Now for SN1. Here, the 1 stands for unimolecular. This is huge because the rate depends only on the concentration of the substrate. This one happens in 2 steps. In the first slow step, the halogen just leaves, forming a carbocation intermediate. Then in the second, much faster step, the nucleophile attacks that carbocation. This is your money slide. Seriously, pause here, take a screenshot, and use this for your last-minute revision. Let's recap. SN2 is one step, no intermediate, and favored by primary halides. SN1 is two steps, forms a carbocation intermediate, and is favored by tertiary halides. SN2 needs a strong nucleophile, while SN1 can work even with a weak one. This is your ultimate cheat sheet.
So far, we've pretty much been looking at molecules on a flat 2D plane. Now let's add a really fascinating 3D twist and talk about a very cool concept called optical isomerism.
So, what exactly is chirality? Well, it's a property. If a molecule cannot be perfectly placed on top of its mirror image, if it's non-superimposable, then we say it's chiral. In organic chemistry, this usually happens when a carbon atom is bonded to 4 completely different groups. That carbon then becomes a chiral center.
The absolute best way to understand this is to just look at your own hands. They are mirror images of each other, right? But try to place your left hand perfectly on top of your right hand, palm to palm, thumb to thumb. You can't, can you? That's exactly what chirality is. It's simply handedness.
So these pairs of non-superimposable mirror images have a special name, enantiomers. They have all the same physical properties except for one very cool difference. When you pass plain polarized light through a solution of them, one enantiomer will rotate the light to the right, or clockwise. We call that dextro, or D, and the other will rotate it to the left, or counterclockwise, which we call levo, or L. So now that you know all the rules, here's a final question for you. If you have a tertiary alkyl halide and you put it in a polar solvent, which mechanism is going to dominate, SN1 or SN2? Think about it. The answer lies in everything we've just discussed. Remember these key concepts and you'll be all set. All the best for your exams.